In this lesson, the interfaces, the structure, as well as the most important elements of a control chart are explained. And hello again to this lesson, which essentially has two learning objectives. In the end, you should have understood that the control plan has interfaces to other documents and quality assurance methods, such as the FMEA. And of course, you should know when and how a control plan is used and what elements it contains in order to then be able to create one yourself, or to collaborate in the creation of one, or just be able to use it properly. This lesson is divided into two chapters. In the first chapter, we look at some interfaces to the FMEA. In the second chapter, the control plan from the first chapter is developed further and the various elements are explained in more detail. Let's start with the interfaces between the FMEA and the control plan and start the creation of the control plan. At this point, it must be assumed that basic knowledge of the FMEA is already available. If this is not the case, there are separate lessons on product and process FMEA available. A small excerpt from one of these FMEAs is shown on the left. Any product or process can be broken down into smaller elements, commonly called system elements. This section of the FMEA contains some system elements. Firstly, a buckle, meaning the buckle of a seatbelt in a car. Then a bracket, which is a subassembly of the buckle. And finally, a process element for the riveting process. Functions and/or characteristics are assigned to these system elements. One characteristic of the buckle is that it must withstand a braking load of 20 kN. If we now look at the first part of the control plan on the right-hand side, it begins with the process elements. What was a process element in the FMEA becomes a process element here in the control plan. Accordingly, the system elements buckle, bracket, and the process element forming the closing head of the rivet can be found here. If a machine is required to produce a characteristic, then this is to be inserted here in the column Machine, preferably with a more detailed machine description. This is followed by the two columns Product Characteristic and Process Characteristic. As can be seen here, the characteristics are taken directly from the product or process FMEA. For the buckle, it is the braking load. For the riveted subassembly bracket, it is the rivet length after riveting. And for the riveting process, this is the forming of the closing head. It is the travel of the rivet head maker to an end position Z. In the product FMEA lesson, the meaning of failures was explained. Also, what classification of failures or characteristic means was discussed in more detail. Only briefly so much here. Depending on the severity of a function or characteristic, it can be classified as critical or significant, abbreviated by CC for critical characteristic or SC for significant characteristics. It is important that such special functions and characteristics are identified as such in all documents involved in manufacturing or monitoring. In column C, C for classification, the characteristic braking load and rivet length are marked as critical characteristics, just like in the FMEA. To be able to produce and monitor these characteristics, they must of course be specified. These specifications for the product characteristic or process parameter are reproduced here in this column. Greater than 20 kN for the braking load, or 12 mm plus minus 0.2 mm for the rivet length after the riveting process. These specifications should always allow for variable or attributive testing. After we have just transferred the first data or information from the FMEAs to the control plan, we now continue purely in the control plan with the methods and reaction plans. All columns of the control plan are shown here. On the left is the content from the first chapter, which comes from the FMEA. To the right of that, we have the columns for the methods. Methods in this case is everything that would be needed to check the characteristics or functionality. This includes the test equipment, information on the size and frequency of the sample, and the control method, which we will go into more detail in a moment. The reaction plans will then be found on the far right. As far as the header of the control plan is concerned, let's limit ourselves to stating that it must contain the usual information on the company, product, responsibilities, release status, and the like. The characteristics or functions listed before must of course be checked. The test equipment used for this must be listed here for each characteristic. A test can be carried out subjectively through a person's sensory perception or through objective tests. Measuring and gauging fall under objective tests. These test equipment should be subject to test equipment monitoring, and it must be suitable for the intended purpose and use. This means, for example, that the measuring range, the resolution, the precision, the measurement stability, etc. must be suitable. Such proof can be provided, for example, by a capability study for the test equipment. Keyword MSA for Measurement System Analysis. For our example, a tensile testing machine with a measuring equipment number P23.2 is used to check the braking load, and a digital length measuring system is used to measure the rivet length, etc. Next, it must be determined how often a feature must be checked. Of course, one must consider whether it's a destructive test or not. With destructive tests, such as for the braking load, you can of course only check random samples. The determination of the sample size and the frequency must be based on the severity of the failure effect, the probability of occurrence, and the probability of detection of a failure. For this, you must again look at the FMEAs. Measures for monitoring the characteristics should already be defined there, considering the failure assessments. The FMEA could have shown that it is sufficient to subject 10 of every 10,000 parts produced to a static braking load test. Or, as here for the length of the rivet, testing of 100% of the parts could be required. The control method is the method by which the test process is controlled. This could be, for example, procedural instructions. Procedural instructions are any kind of binding internal company guidelines and regulations. For example, work instructions or test instructions. A maintenance plan can also be included. In the response plan column, it is, for example, entered how an employee has to react if a defect has occurred. For example, it can be stipulated that the production must be stopped immediately. Batches can be blocked, or defect parts can be reworked or scrapped. An 8D report can be started, or the information that a failure has been detected simply needs to be passed on. Responsible persons or positions should also be named. Finally, we come to the question of when a control plan should be used. A distinction is made between three phases, in which the methods and reactions differ. A control plan can be used during the manufacture or testing of prototypes, or during a pre-series. With these two, the sample size and the sample frequency will certainly be higher than during series production in the series control plan. So, one differentiates between prototype control plan, the pre-production control plan, and the production control plan. Well, that was a lot of new information. Therefore, I would like to conclude by repeating the 3 most important key messages. Control plans are applied in the following 3 phases: prototype build, pre-launch, and production. The control plan controls the internal manufacturing process. The production structure is shown with the planned test procedures. The control plan specifies measures if a failure occurs. If you found this lesson helpful, please let me know and leave a comment. Thank you for that. Take care and see you next time. Bye.